Now, if we heat that up, look what happens to my curve. Okay, I want to heat up this tiny little amount of silver by 1 degree. How much energy do I have to put in? So T is T final minus T initial, and that would be in degrees C. First of all, let's just define temperature, and you may have this definition in your book. It is a measure of the average kinetic energy of particles. So if I have a sample, what I want you to know is if there is an average temperature here, or a temperature, there is an average speed of particles. But in a sample, not all of the particles are moving at the same speed. Some particles are moving at this speed, a lower number are moving at this speed, and then a very few are moving at a high speed. Okay, so temperature is just an average of that. Now, kinetic energy, you don't really need to know this equation, but I think it's important that you know that kinetic energy depends on the mass of the particles, which they're tiny, and the speed. V is velocity or speed. So the faster particles are moving, the higher the kinetic energy, the higher the temperature. So I have a little glass of ice water here that is at 0 degrees C. What does that mean? That means that the average temperature, the average of the speed of the particles is right here. Now, if we heat that up, look what happens to my curve. Okay. If I add heat, I get those particles moving faster to where the average is right there. Okay, makes sense? Temperature is dependent on the energy of the particles. Now, let's go on to the Kelvin scale. Kelvin is our SI-based temperature unit. Thermometers are in Celsius, and then you convert that to Kelvin. So let's say we had 100 degrees Celsius. That would be 373 Kelvin. Now, the thing to remember is that Kelvin can never be negative. Celsius can be negative. For example, let's say we had a temperature that was 253 Kelvin. What is that in Celsius? Well, we need to subtract our 273 and we get negative 20 degrees Celsius. Remember, Celsius can be negative, but Kelvin not. Now that will be important when we do some calculations later in chemistry. So that's the Kelvin scale. Now let's talk about heat. Heat and temperature are not the same thing. Heat is energy that flows. Why does it flow? Because there's a difference in temperature. So let's say I had a substance that is 50 degrees C on this side, and it comes in contact with some water that is at 10 degrees C. Well, the heat is going to flow from hot to cold. Okay, that makes a lot of sense. Now, our unit for energy is the joule that we're going to use for heat energy or chemical energy, all kinds of energy. A joule is a very small amount of energy, and so we often use the kilojoule, which is 1,000 joules. Now, let's relate heat to the amount of substance. There is a term that you may have seen called specific heat capacity. And it's how much energy it takes to raise a gram of a substance by 1 degree C. So let's say I have 1 gram of silver, and I have it at 10 degrees C, and I want to raise it to 11 degrees C. Okay, I want to heat up this tiny little amount of silver by 1 degree. How much energy do I have to put in? Well, that is the answer right there, the specific heat capacity. And on this little table, there are obviously specific heat capacities for lots of substances, but I have a few here. Water has a particularly high one. Let's use that in a problem. This is what we call the calorimeter equation. Let me define the terms and then we'll work a problem. So Q is the heat it takes in joules. M is the mass of the water, and that would be in grams. Specific heat we just saw, that is in joules per gram degrees C. And then temperature, delta T, is T final minus T initial, and that would be in degrees C. Okay, so temperature change, how much heat is related to the mass of water that you have. So here is a little problem. We want to find the amount of energy, so we're looking for Q, to raise 45 grams of water, that's my mass, from 15 degrees, that's initial, to 27 degrees, T final. Okay, so delta T is 27 minus 15, which is 12 degrees C. All right, here we go. Here is our Q is equal to the mass times the specific heat, which I'm going to grab off of this table. There it is for water. And that would be 4.184 joules per gram degrees C. All those units go with it, times my delta T, which is 12 degrees C. Now, watch what happens when we multiply. Grams on the top cancel grams on the bottom. Degrees C on the top, degrees C on the bottom. I'm left with joules, and Q is equal to, let's see, 2,300 joules. That's how much heat it takes to raise the water temperature. Now, if we wanted to raise the temperature of a larger quantity of water, it would take more heat. Or if we wanted to go to a higher temperature, more heat.